This is a video that's going to look at two-slit interference. Two-slit interference is an interesting light phenomenon. It's a wave phenomenon specifically. So if I have some kind of a blocker over here with two slits in it, appropriately named, and those are separated by some distance d. I'm going to have a screen over on this side that is pretty far away. So I'm going to call this distance L. I know a lot of times they call it a capital D. I don't really like using an uppercase and a lowercase letter to mean two different things in one equation, so this is what I'm going with. I'm going to rewrite this one as just the slit separation equals D. Now if I've got some kind of a light source, let's go with a light source back here. That light source is putting out waves. Those then hit these slits, and each one puts out waves. So I want to look at what's going on with this. What I would find first, this is just a line going right to the middle. So a right angle, this is kind of my central line. What I would find over here is that I get a spot that's really bright right here in the middle on the screen. I would see a very bright spot, but then I see a dark spot. And then I see another bright spot over here. Not quite as bright as the first, but still a bright spot mirrored on the other side. And then a blank space. And then another bright spot. And another bright spot. And I see this recurring pattern. These would be called bright fringes. And in between there we have dark fringes. I'm also going to have a way of labeling what these are. And it can be any letter for an index. Sometimes you see N, sometimes you see M, and I kind of try and avoid using both of those. I'm going to just call these I's. So this is my I equals 0, I equals 1, I equals 2. This could be like an I equals -1. And I equals -2. I'm only trying to avoid using N because once you start combining index of refraction, or once you are doing light things and you have an N for index of refraction, then to reuse that variable right now, it turns out that it causes a bit of a hang-up from time to time. So I want to see what's going on with these bright fringes. Looks like this. If I have a light ray that's coming in from here, that has to travel a certain distance. A light ray coming from this slit also has to travel that same distance. These travel the same distance as each other, so my difference in the path length, I used L up here already. I'm going to change that L to something else. I'm just going to change that to an X. The difference in my path length that I travel, in this case, is going to be 0. What I do know is that the waves that are coming in here, right, again I said these are kind of starting over as waves again. These are in phase with each other, which means if I take a picture, the moment that this is coming through here, I would have wave 1 is going to look like this. This is the oscillation versus the position. That would be my wave 1, and wave 2 is going to be right in line with it. When this happens, these waves are called in phase, meaning the peak of one wave is coming at the same time as the peak of another. Sometimes it's easier to see what it looks like when these are out of phase. When these are out of phase, they might look like this. This would be out of phase with the yellow. The in phase and out of phase describes a relationship, so it can't be like one thing is in phase. You have to talk about how two waves are in relation to each other. So these two yellow waves are in phase with each other. The yellow and the red are out of phase with each other because when the one is at a peak, the other one's at a trough. That's all that means. Now we have seen from light interference that two waves that are in phase with each other, these will add constructively. We saw that back when we were doing interference of waves, looking at resonance on strings even. Two waves that are out of phase, these are going to add destructively, or if you like, subtract, right? So these will add destructively and kind of cancel each other out. These will add constructively and not cancel each other out. At this central line, I've got two waves that are traveling the same distance as each other. Of course, they travel the same speed as each other, so if they travel the same distance and the same speed, and they start off in phase, they're going to end up in phase. And that's why I get a bright central maximum. But that's not always the spot that I'm looking at. I want to look at a couple other spots too. So let's see what happens with this first bright fringe. With this first bright fringe, I've got these two lines going on, and I'm just going to draw a line from here to here through the center of this thing. It's going to be helpful later. So I've got these two lines going on, and now I get a path length difference that's not equal to 0. This top wave doesn't have to travel as far as the bottom wave. In fact, I can figure out just how much of a difference there is by taking this thing and cutting it. I'm going to cut it with a line that's perpendicular to that central white line, to the diagonal central white line. And that's going to make this into an isosceles triangle. This side and this side of my triangle are the same, but there's a difference that comes in this side and this side are the same, but there's a difference that comes in right here. So I'm going to take this whole region and blow it up a little bit. We will come back to what's going on out here, but I just want to look inside this blue box. So inside this blue box, what I have a space like this, and I have my separation distance. I said I had one wave that was going out this way and another wave that was going out this way, and I had a line down the middle of those. So the first thing that I did was cut right here. When I cut right here, with this being a right angle, and this is some angle theta, right? When I cut here, I am making an isosceles triangle out of this piece, right? That's going to keep going for however far, there and there. That's going to be an isosceles triangle. And what I would like to do is take a look at just this path length difference here. So that difference, what I do know right away, is that the distance between these slits I said was equal to D. So I would like to look at this right triangle. I'm going to say here. This thing, this, and here. To be completely fair, this is not actually a completely right triangle because these two rays, this one and this one, aren't parallel. But because that screen is so far away relative to this distance, those two rays are almost parallel. The angle difference between them is going to be small enough to where we won't even notice. So I've got this, I've got that D, and this is the side that I'm really interested in, is right here. This is my path length difference. From this triangle, I can say my path length difference is going to be equal to D times the sine of theta, because of all kinds of angles, right? Here's theta, so here is theta, and if that's theta there, then this has to be theta up here. Those angles have to match. So my path length difference is equal to D times sine of theta. These two waves, they start off in phase with each other. If their path length difference is 0, then they stay in phase. If their path length difference is equal to a wavelength, then what's going on? I've got wave number 1 that's doing this, peak 1, peak 2. I've got wave number 2 that's doing this. Where this is peak 1 and this is peak 2. These waves, they don't actually care whether they're on peak 1 or peak 2. What they care about is, are their peaks lined up or are they opposed to each other? They're lined up. So even though these have a difference, a path length difference of one wavelength, they're still going to be in phase. So a path length difference of a wavelength puts these in phase. And it might not be fair to say that they stay in phase, it's more that they're in phase again, I guess, because it's not the same part of the same wave. Now, what if this is shifted farther? What if this is shifted by 2 wavelengths? Then this is now peak number 2, and this is peak number 3. And there's a peak number 1 back here. We're still fine. So if my path length difference is 2 wavelengths, we are in phase. And really that's true for any whole number of wavelengths. So if my path length difference is any number of wavelengths, I end up in phase. With I equals any whole number. So let me see what that looks like. I'm now saying my path length difference, if that's equal to a whole number of wavelengths, I end up in phase and I get constructive interference. So d sine theta equals I lambda gets me there. I want to look back at what this means here, and I'm going to do a little bit of erasing because this got really busy really fast. Let's get rid of this too. What I did, I said I had over here at this center line a path length difference of 0. if I go out to this first maximum, I have a path length difference of lambda, or 1 lambda, if you like. And that's what makes that my I equals 1 maximum. If I go out to a different spot, out here, I get a bigger path length difference because this top wave is traveling this far, the bottom wave has to travel even farther to catch up. That's a path length difference of 2 lambda, which is why that's my I equals 2 maximum. This first one is my I equals 0 because there's no path length difference. So that takes care of my bright spots, but what's going on with the dark spots? With the dark spots, I'm looking at something a little bit different. I still have the same interference thing. I still have the same, this is my path length difference. But if I get a path length difference of half a lambda, now I'm out of phase. If I get a path length difference of 1.5 lambdas, I'm out of phase. And so on. If I get a path length difference of a whole number plus a half lambda, right? I is still a whole number, then I'm out of phase. Going back up here, what that means, and I labeled my bright spots up on top, I will label my dark spots down below. What this means is that I can get a dark fringe right here at the halfway point between. And for that one, my path length difference is going to be half a wavelength. If I want my next one, I'm going to get a path length difference of 3/2 wavelengths. So I can pick out my dark spots. This was my I equals 0 central max. This one is going to be my I equals 0 minimum, because I'm going to say this is 0 plus a half times lambda. My green one was 1 plus a half times lambda, which makes this my I equals 1 minimum. Trying to put these pieces together a little bit and summarize them because the pictures get pretty busy and the equations get pretty busy. What I found, my path length difference, which is equal to d times the sine of theta, is equal to, if it's equal to a whole number of wavelengths, I get a bright spot. If it's equal to something and a half wavelengths, I get a dark spot. And that's really it for two-slit interference. I'll make sure to give you an example video working through one or two of these, but that's the principle.